In this activity, what I want to do is talk about types of functional programs in general, and how they work out for programs that we write in Erlang. Okay, let me just explain what I mean by a type. In general, a type classifies a set of values. So, for example, 0, 1, 2 are integers, and true and false are booleans, but 0, 1, 2 are not booleans. And we classify things according to what we can do to them. So, for example, we can take the OR of two booleans, but not the OR of two numbers. We can add two numbers, we can't add two booleans. So we can perform different operations on things of different types. And the functions that we write ourselves can themselves be given types. So we saw a few sessions ago that we can write a function sum that takes a list of integers and gives us back an integer. So types classify values, and the functions that we write can be thought of as transforming things of one type or a number of types to a given type. Now, if we carry on with the sum example, takes a list of integers to an integer, then it's an error to apply sum to true or to the list true and false. It's also an error to take the length of its result, because it's an integer, it's not a list. So this sort of error is one that in principle is easy to discover. We don't have to know that what particular list of booleans we have in order to know that we can't apply sum to it. So it's possible, and some languages support this, to make sure that any type error that a program contains is caught at compile time. We don't have to run the program in order to find the error. And many functional programming languages, Haskell, OCaml, ML, F#, are strongly typed in this sense. Type errors are caught at compile time without running the program. Now, in weakly typed languages, and Erlang is one of these, and the whole Lisp family of programming languages are others, program errors which are to do with types may well only be detected at runtime. So you've written a program, you've done something, you've added two booleans together, you only discover that when you run the thing, and that's not ideal. So what can we do to try and help? Well, the answer is that we can use some tools to come to the rescue, or at least partially. Erlang isn't strongly typed, and we'll say a bit about this when we get to an example a bit later on. So, although it isn't built in, it's possible to add type annotations to programs, specifications, and it's possible to check for some type errors statically. Using the tool Typer, which is built on top of the Dialyzer tool, which is to do general correction of Erlang errors. It analyses for discrepancy errors. Discrepancy analyzer is condensed to Dialyzer. Now, the sorts of types that Erlang contains are, we've seen already, but let's just describe them briefly, or a subset of them. Integers and floats, generally numbers, type of atoms, type of booleans. We can build types for tuples. So tuple types look like a tuple of types, and each type describes the values that go into that slot in the tuple. And we have lists which are we think of as being homogeneous, so a list of type T, though there is always the Erlang type any, so list of any can contain elements of whatever type you like. String, which is an abbreviation for list of characters. And we can say things are of function type. This is something we'll talk about next week. We can just say it's a function, or we can say very specifically it's a function that takes things of type T1 up to Tn and gives us back something of type T. Now, if we want to use Typer to analyse a file or a collection of files, it's really easy. We just put on the command line Typer and the name of the file. As I said, Typer is built on top of Dialyzer, and Dialyzer itself has some persistent data that it uses to speed up its analyses. Dialyzer works by analysing all the Erlang codebase that you might be using, including the Erlang system itself. And so what it needs to do is build this persistent database of information when you first run it. And this is what we're doing here, building the so-called Dialyzer PLT. And as you can see in the lower half of the screen, it took 1 minute 14.49 seconds. It takes quite a long time to run. That's because it's building this huge structure, analysing it, and so on. But once it's done once, you never need to do it again. And so you need to do that, and then we can use Typer as you see it here. Let's look at some examples, and let's look at the particular example of the palindrome program that we devised a few sessions ago. On the right of the screen you see the naive palindrome, palin, which simply checks to see whether a list is equal to its reversed version. On the left of the screen you see the more sophisticated version that first removes the punctuation, then turns capitals into small letters, and then does the am I equal to my reverse check. So there we've got our program. What happens when we apply Typer to that? What we get back is the specifications that Typer can derive. So these are the things that applying this will permit. Now actually, if we want to give a more restrictive specification, we can say we know that if we apply palindrome to a string, we'll get a Boolean. And if we do that and then run Typer again, you'll see that Typer accepts that spec because it's the one that we have specified. It only accepts it if it is consistent with what it already knows. In a similar way, we can say that nopunct takes strings to strings. What Typer derived, it takes a list of any to a list of any. We're giving it a tighter type there. We're saying we know if we give it a string, then it will return a string back to us. And again, Typer is happy to accept that. If we say something like nocaps takes a string to a Boolean, that's not consistent. You can see it says error in the contract of function where nocaps. The contract is string to Boolean, that's what we said it took, but the inferred signature is list of any to list of any. And that's not consistent with what we saw there. So Typer doesn't accept that. We can still compile it, Erlang still accepts it, but Typer has analysed for us the fact that our annotation is incorrect. Now if you take a look here, I've added a test which applies palindrome to a list of atoms. And what happens if we call that? You'll see that this gets the type test has type none. That's because this is, we would hope it would have a result Boolean, but that's because it's inconsistent. It can only be okay if we apply it to if the function never terminates. But in fact, it's saying, if you like, type error there. Now for a final example, let's look at saying that this is the type of nocaps. It takes list of atom to list of atom. If you see what happens here, Typer is happy to accept that. Now why should that be? Well, the answer is, what restrictions are there on the type that nocaps takes? Well, it takes a list and it applies nocap to every element. Fine, that doesn't restrict anything in itself. But what about the type of nocap? If you look at that, it looks as though what we're doing, at least in one half of the case statement, is we're adding 32 to x. So x must be a number. So in the case that x is in that range, x is a number. The problem is that Erlang's ordering applies to any, we can compare any two values together with the ordering. So the ordering doesn't restrict X at all. And so in the false case, we have no restriction. X could just be of any type. So the saying that it takes list of atoms to list of atoms is not inconsistent with the type that we had there. However, if what we do is force it to return a number on both arms of the case, by doing this, we now get an error. Typer has managed to infer that it's no cap takes numbers to numbers, and so no caps takes a list of numbers to a list of numbers, and that is not consistent with the contract of taking a list of atoms to a list of atoms, a list of atoms to a list of atoms. Okay, so we have that error there, but only when we change to force X to be a number. We could explicitly say we wanted X to be a number. That would be perfectly reasonable too. Erlang allows you to do that. But it's not the case that Erlang is as strongly typed as a language like Haskell. Another thing to be aware of, and this is my last remark, just because we've specified that no punct takes a string to a string, that doesn't mean we can only apply no punct in the future to strings. We can apply it to a list of any type, in fact. The contract, if you like, the spec contract simply says if we give it a list of strings, we get back a list of strings. It doesn't say anything about what might happen in any other case. So these specs do not restrict the type of the function. They simply describe what it should do when in particular circumstances. If given a string, it returns a string back. So these are what are called success types. They are they're more permissive than types in other languages. You only get a type error when it's impossible to run the program without an error being produced. That is, if you like, the dual of what normally happens with types, that if there's any way of it producing an error, you are told that because it's been caught at compile time. Success typing is the dual. It will say, it will only give you an error at compile time when it is certain that it will cause an error at runtime. So it's more permissive, but it means some type errors we might like to catch are not going to be caught. Now this is just a brief introduction to typing. You can see there is the tool there, but if you want to find out more, in Francesco and my book in chapter 18 there's quite a lot more about Erlang types, and in Fred Eber's book there's a chapter on it, and also that chapter is available online. So that gives you quite a lot more information about Dialyzer, how it works, what are the advantages and perhaps some of the limitations of using it. Okay, so that's it for this section. Of course, what you might like to do is try working with this yourself in some of the examples you've written. Try including type specifications, see how they behave with Typer, and so on, to get some experience of how it works. Okay, but that's it for this section, and in fact for this week. So what we'll look at next week are higher order functions and a whole lot more by way of examples. Okay,